In the past few lessons, we have been integrating functions to approximate the area under the curve. In turn, we have used that area to compute pi. This slide shows the integration of a quarter circle. We also integrated this function. A bit of trigonometry and calculus tied it back to pi. Next, we are going to venture into the realm of statistics. If you've ever taken a statistics course, you've probably heard of the normal distribution, which looks quite similar to this. The total area beneath that curve is equal to 1. Well, what if I multiply both sides by the square root of pi? I can also exploit the property of symmetry to divide that value in half, as reflected in the lower limit, which changes from negative infinity to 0. I omit the details here, but it can be shown with calculus that the integral of e to the negative x squared, from negative infinity to positive infinity, is in fact equal to the square root of pi. Perhaps another day we can hash out the details. Squaring both sides of that gives me pi over 4. Multiply both sides by 4 and we've isolated pi. So what's the deal with this integral in the square brackets anyway? This is the function we are going to numerically integrate using Simpson's rule or Romberg integration. Of course, we cannot start or end at an infinite value using a finite machine like a computer, so we're going to have to pick an endpoint close enough to infinity to make it work. Visually, that bell curve looks like this. You'll remember from statistics class that not much happens beyond x equals 3. The tails are pretty flat out there. Not much area beneath them beyond that. A while back I mentioned symmetry. That basically means instead of integrating from negative 3 to positive 3, I can simply integrate from 0 to positive 3 and then double the result. The area in both cases should be the same. It looks like that approach had a promising start, but then tapered off quickly around 4 digits of accuracy. So what do you think happened? My suspicion is that we didn't include enough of the tail region, despite our assumptions from statistics class. Instead of negative 3 to positive 3, let's try integrating from negative 6 to positive 6 and see what happens. Using symmetry once again, I can actually integrate from 0 to positive 6 and double the result. That looks something like this. Another promising start. This time it tapers off around 14 digits of accuracy, which is approaching the limits of this software anyway. Here are the function evaluations for 1, 2, 4, and 8 panels. The same pattern continues for more panels. Using Simpson's rule, we obtain 14 digits of accuracy with a mere 32 panels. That's not bad at all. Here is the data for Romberg integration. The most accurate approximation is almost always in the first column, which effectively means we are only using the trapezoid rule. For some reason I haven't quite figured out, Romberg integration isn't helping us out this time. If you have any ideas why, feel free to post them in the comment section below. Once more, the base 10 logarithm gives us the number of digits of accuracy. The highest values occur almost exclusively in the first column, as we just saw. The two methods are compared side by side in this slide. This is the data that was plotted previously. Using Romberg integration, or technically the trapezoid rule in this case, we reach 14 digits of accuracy using only 16 panels. Thus far, this seems like the fastest converging approach we've looked at. That's all well and good, but before you get too excited, there are a few things to consider. One of those considerations is the computational complexity of your function evaluations. What's that supposed to mean? Well, computational complexity is a way to measure how long it takes a computer to perform an operation. So in general, addition and subtraction require the least amount of time. A little more time is needed for multiplication, division, and root extraction. which depends on multiplication and division if you use an algorithm like Newton's method. More time still is needed for exponentiation, seen in the rightmost column. I should mention that time is not the only factor involved in computational complexity. The amount of memory needed to store digits and intermediate values is also an important consideration. This topic can become complicated very quickly, so for now, I'll try to keep it as simple as possible. Using those general trends, however, it can be seen that integrating the circle and 1 over 1 plus x squared are about equivalent in terms of computational complexity. Integrating the Gaussian curve requires exponentiation, which is more computationally complex. So even though it gives us many digits of pi with fewer panels, a more thorough analysis of computational complexity would be needed to determine if it truly was faster in the end. That is beyond the scope of this lesson, but for now, I want you to be aware of these considerations. Another potential hang-up with integrating the Gaussian curve are the infinite limits. We got away with -6 to +6, but if you wanted more than 14 digits, you'd have to keep going further and further. At some point, that approach may break down. I don't know for sure, but that's another consideration to keep in mind. In case you were wondering why exponentiation is more computationally complex, here's a quick demonstration. This is the Taylor series expansion. X to any power can be thought of as repeated multiplication. So for each term, many multiplications are needed. Then these terms are added together. So cumulatively, that all makes exponentiation take more time than the other operations. Of course, that is a very simplistic way of looking at things. In practice, we can use various tricks to exponentiate numbers more efficiently than just plugging them directly into a Taylor polynomial. Perhaps later I can elaborate more on these matters, but for now, I leave you to ponder them for yourself. For the time being, that's all the more I'm going to talk about integrating functions to find pi. If you can think of any other functions we could integrate, please let me know in the comment section below. Otherwise, our next lesson is going to take a different approach to calculating pi. Stick around for that. I look forward to seeing you next time.